Hello everyone and welcome to this video. Today we're gonna cover Green's theorem and we're gonna go through it, have some examples, solve some examples, and we're gonna basically this is a short video on Green's theorem. So what is Green's theorem? So let's read the definition. So it's saying let C be a positively oriented, piecewise, smooth, simple, closed curve. So C is simple. So what simple means is basically a curve that's not closed. It's a curve like this. So a not simple curve would look something like this. So this is a not simple curve. This is a simple curve, okay, and this is a simple curve. So it's saying that C is a simple, smooth curve, okay, so there are no cuts in it, and it's a closed curve. And also, so this is our curve, and he's saying also let D be the region enclosed by the curve, okay. So let D be a region enclosed by this curve, and so if we have P and Q continuous first order partial derivatives on D, then we have this. We're gonna have the integral of P dx plus Q dy, which is the double integral of the partial derivative of Q with respect to x minus the partial derivative of P with respect to y times dA. So that's basically Green's theorem. So P dx plus Q dy equals the double integral of d Q over dx minus dP over dy dA. And so this is example 1. So we need to use Green's theorem to evaluate this integral, where C is the triangle with vertices 0, 0, 1, 0, and 1, 2 with positive orientation. And so basically we can say here that P is equal to xy and Q is equal to x squared y to the 3. This is Q. And then, okay, so this is C. And so let's say C is a triangle, okay. So actually a simple curve can be closed, okay. Or just let's correct this. A simple curve can be closed, but it cannot be something like this. It cannot intersect itself like this, okay. So it's a piecewise smooth curve, and it's a closed curve. So it is a closed curve, but simple, not, and as you can see, it's simple and does not intersect itself two times, as you can see. And so these two are simple curves, and this is not a simple curve, and so it should be a closed curve. So simple, not simple. And so this is the triangle, and our vertices are just, so let's say this is the xy axis, and so 0, 0, and we have 1, 0, and we have here 1, 2. So we have P and Q, x squared y cubed. Okay, so we need to use Green's theorem to evaluate this flux, as you can see. So we are calculating the flux now, or this integral, okay, line integral. This is a line integral. So basically you just do double integral of dq. So this find qx, so qx partial derivative, so 2xy to the 3 py x, as you can see, and double integral. Now we do qx, which is 2xy to the 3 minus py, which is x dA, and let's say just we will start with dy dx, okay, and then over the region. So for the y, as for the y, we're gonna have it from 0 to 1, and for the x we're gonna have it, so xy on 0 to 2 actually, we're gonna have it from 0 to 1 here. So 0 to 1, 0 to x, 0 to 2, as you can see. Okay, so that's the integral to xy to the 3, yeah, xy and 2. And that's basically how we evaluate it. We just need to evaluate this double integral. we evaluate this double integral, and then we find the value of the line integral there. And so let's see our other example. So actually let's just double check our y. So maybe we do it like in polar or in other coordinates. Let's go to example 2. We'll come back to this and check the boundaries. I need to make sure the boundaries are correct, but overall this equation should be correct. Okay, and so let's evaluate this. So here q equals y to the 3 and p equals minus x to the 3. And so r equals 2. And so basically let's find qd, or actually this is p and the other one is q, so step opposite. And so here we do have px, and we need to find py, sorry. So py is just 3y squared, and then qx is just minus 3x squared. So we have the double integral of qx, which is the partial derivative, minus 3x squared minus 3y squared dA. Now this is a circle. It has a radius of 2, and so we can basically say, okay, so it's center at the origin, so 2 0 0, and we have 2 0 2 2. Okay, we have 2. Okay, and that's basically it. Now the equation of this circle is gonna be y squared plus x squared equal to 2, and now we have dx dy. Okay, so and x equals square root of 2 minus y squared, so plus minus, so it goes from minus square root of 2 minus y squared and goes up to 2 minus y squared. And now as for the x, is gonna be basically from negative 2 to 2. So if we let y equals 0, we're gonna have just x equals plus minus so this is 4 actually. This is 4. That's plus minus 2. And now this is basically how we find this integral. So yeah. Okay, so as for here, now let's come back to this. So basically let's do it in polar. So as you can see this, and then let's do this in polar. So now we're gonna just convert everything to polar. So 2 times x, so 2r. Okay, so yeah, so 2r cosine cosine theta multiplied by r sine theta minus r cosine theta r dr d theta. And that's basically our double integral. Now let's do it in terms of r. So r is changing. So if we want to find the equation of this line, so it's gonna be just y equals so y equals basically so y2 minus y1. So m, the slope, let's find the slope. The slope is y2 minus y1. So 2 minus 0 and 1 minus 1. So yeah, 1 minus 1. Okay, so basically this is not like this, so it's gonna be something like this. See, yeah, so it's gonna be something like this, so it's gonna be simpler. So here we have this line is x equal 1, and x equal 1 is just r cosine theta equals 1, and so r equals secant theta. Okay, so r is gonna go from 0 up to secant theta, and basically here we have, let's simplify this, 2r to the 4 cosine theta, okay, qx sine to the 3 theta, and then we have p, which is just r cosine theta. And yeah, so that's basically it. And we also, okay, so as for theta, now theta is gonna go from 0, okay, and it's gonna go up to so here we have 1 0, and we here have 1 2, and it's gonna go from here, and basically so theta is equal to tan inverse of, so we want to find the theta here, it's theta, so it's gonna be y over x, so 2 over 1, theta equal tan inverse of 2, and tan inverse of 2 is just gonna be, let's find tan inverse of 2, it's gonna be just some number, okay, yeah, it's gonna be just some number, and so it's gonna be just, you know, tan inverse of 2. We say it's from 0 up to tan inverse of 2, and that's basically how we do it in polar. Now let's evaluate example 3. Okay, so we'll do the same basically. It will be the same, so let's just skip this. So he wants us to also find the circulation around the circle. Okay, so yeah, so now let's see here. So if you use Green's theorem in reverse, we see that the area of the region D can also be computed by evaluating any of the following integrals. So these are the integrals. A equals the integral x dy equals minus the integral y dx equals half of integral x dy minus dy. And so yeah, so we can find the area if we reverse the Green's theorem. And he's asking us to use Green's theorem to find the area of a disk of a radius a. Okay, so he wants the area of a disk. What is a disk? It's basically this. Okay. So the disk has radius a. Okay, so this is our disk, and we have it of radius a. Basically, if we want to find the area, is gonna be a, and it's basically this cx dy equals minus the integral of over the curve y dx equals half of the integral of x dy minus y dx. So this is example 5, as you can see. Okay, so basically x squared plus y squared equals to a squared, and so x is just square root of a squared minus y squared. So basically it's gonna be here. So a equals the integral of a squared minus y squared dy, and that's basically the area of a circle with radius a. Okay, that's basically it, and we can do it in terms of x or even xy, and that's basically it. So example 6, evaluate the integral, okay, the line integral over the curve c, 3y minus e to the sine y dx. Okay, so and the curve is a circle of radius r and centered at the origin, and so now we have p equals 3y minus e to the sine y. Okay, and then we have q equals 7x plus square root of y to the 4 plus 1. This is q, or actually it's the opposite, so qp, and qx is gonna be just a q, is it y or x? so it's gonna be here d. So we have p dx. We have this q 3y e to the sine root y dx. We have 7x y to the 4 this one. As you can see, this is qx. And okay, so it's gonna be 0 qx, and py is gonna be just 2 square root of y to the 4 plus 1 and 4y to the 3. And that's basically our py and qx. And now in order to find the integral, we just subtract them, and so we're gonna have the integral, as you can see. So qx minus 0 minus 4y to the 3 over 2 square root of 4y to the 4 plus 1. And then we have multiplied by dA, so which is basically dy dx, as you can see, like that. And then basically for the y, it's just gonna be, we say this is a circle, so x squared plus y squared equals to 3. So y equals plus minus x squared minus, so 3 minus x squared. And that's basically our y. That's basically our y. And so let's go back. Now it's gonna be from negative 3 minus x squared. Of course, negative is outside. And 3 minus x squared. And then let's let x equals 0. And so, yeah. Minus 4y to the 3, 2y to the 4 plus 1. Okay. Minus. And it's gonna be dy. So I started y, so dy dx. And x is gonna be negative root 3, root 3. And that's it. So example 7, we need to find the work done by the force field. So this is the force field f of xy equals e to the x minus y to the 3i plus cosine of y plus x to the 3 j. Okay, and we want to find the work done. We have, okay, so we have x squared plus y squared, so it travels once over the circle in the counterclockwise direction. So this is clockwise, we want counterclockwise. That's counterclockwise. And as you can see, this is x squared plus y squared. And we also have, as you can see, the counterclockwise direction. Okay, so in order to find the work, it's gonna be just integral. Oh, so he gave us the integral, and we need only to find, so this is the work done. And we can use Green's theorem to find the work, which makes it easier to us instead of evaluating this whole integral and trying to find dx. Okay, we can find dx. Dx is just basically, it's just, yeah, so x is just, so we'll need to substitute r into f. So substitute the unit vector, substitute into f, and then we need to find the dx and dy. So it's gonna make it a little bit complicated for us. So we can use Green's theorem, which makes it a bit easier, and that's the beauty of it. So we have q equals e to the x minus y to the 3, p equals cosine of y plus x to the 3, and then qx equals e to the x, and py equals minus sine of y. qx by, and then we have the double integral qx minus py, so e to the x minus sine of y, let's say dy dx. Okay, and so dy dx, and so we have also a circle, so it's gonna be from square root of 1 minus y squared. No, actually this is y, so it's gonna be x squared. So, and then from minus to positive 1 minus x squared, and then it goes from negative 1 to 1, and that's basically our work. We can evaluate this. Let's try to evaluate this. So the integral of negative 1 to 1 is gonna be with respect to y, so y e to the x plus cosine of y, evaluated from negative 1 minus x squared. Now I run out of space, so basically you're gonna continue with this, substitute in the values of y here, you're gonna get the value for the work here. Okay, and that's it. Thank you for watching. That was briefly Green's theorem. I hope this video was helpful to you.